Imagine standing at the precipice of an infinite abyss, where every pinprick of starlight pierces the darkness like ancient lighthouses across a cosmic sea. In that silence, in that breathless void, you begin to sense it, a presence not of matter, but of scale, a weightless realization that the universe is not empty. It is saturated with time, with mystery, with a history that predates memory itself. And somehow, standing there, a speck on a pale blue dot, you feel not fear, but connection, a strange intimacy with infinity. The sky above is not just a backdrop for dreams. It is an archive of light, an ancient library whose volumes arrive photon by photon. Each star is a time capsule, each galaxy a monument to endurance. But what we see, dazzling as it is merely a fraction, a keyhole view into something far deeper, more intricate, more astonishing. What if behind the visible veil lies a reality so dense with paradox that it could upend everything we think we know about existence? And what if our hunger to know is no accident, but a function of the universe awakening through us? Among the many riddles that populate this celestial theater, none pulls harder on the threads of understanding than black holes. They are the edge cases of physics, the cosmic cul-de-sacs where gravity triumphs so completely that not even light can escape. Long suspected, once invisible, these dark titans were pulled into view in 2019, or rather, their silhouettes were a ring of fire around a shadow, a photograph of absence. To step toward the event horizon is to leave the world of known laws. Inside, space bends so deeply into itself that time begins to twist. The closer you fall, the slower your seconds tick compared to the world you left behind. From outside, you seem frozen. From within, you're racing toward a fate bound by singularity, a word that, in this context, means both unity and unknowability. There, Einstein's elegant equations collapse. The smooth curves of space-time disintegrate into a quantum tempest we can neither simulate nor solve. The universe stutters. And yet, these dark enigmas radiate. Hawking showed us that even black holes are not eternal. They emit ghostly particles, gradually evaporating their mass into the vacuum of space. It is a contradiction wrapped in light, a cosmic confession that nothing, not even oblivion, lasts forever. Some theorists whisper of wormholes hidden within, shortcuts to elsewhere, perhaps even to elsewhens. Others speak of firewalls, blazing boundaries that annihilate any who dare to pass. The truth remains suspended between mathematics and metaphor. Time itself buckles in their presence. Watch someone fall into a black hole and you would never see them arrive. Their image would stretch and fade, their time slowing to a standstill as they approached the event horizon. They would seem to hover there forever, red shifting into invisibility, while within they plunge unstoppably toward a singular core. And not all black holes are equal. Some are the remnants of dying stars, stellar collapses turned gravitational traps. Others are titans that dwell in galactic hearts, with masses millions or billions of times that of our Sun. Sagittarius A, the shadow giant at the core of our Milky Way, anchors the swirling dance of hundreds of billions of stars. These monstrous objects, destructive and defining, are architects of galactic structure. Without them, perhaps no galaxies would form at all. They may also hold the keys to something deeper, the reconciliation of the great schism in physics, relativity, and quantum mechanics. In the abyss, these two frameworks collide, and neither survives intact. A theory of everything must pass through the eye of a black hole. But our cosmic questions do not end there. For all the matter we can see stars, planets, gas clouds, it composes less than 5% of the universe. The rest lurks unseen, inferred only through its gravitational effects. Dark matter, 27% of the cosmic ledger, shapes galaxies like invisible scaffolding. We feel its pull but cannot touch its form. It is everywhere and nowhere. Its story began nearly a century ago. Fritz Zwicky, an astronomer not known for understatement, noticed galaxies in clusters moving too fast to be bound by visible mass. Something hidden was holding them together. Decades later, Vera Rubin confirmed the anomaly stars on galactic edges spin too quickly to obey Newton. Either our understanding of gravity was flawed, or some unseen mass, a dark halo, was responsible. The universe is laced with these halos, forming a vast cosmic web. Galaxies coalesce where the filaments intersect, luminous matter condensing in the gravitational wells carved by something we cannot see. Particle physicists propose candidates: WIMPs, sterile neutrinos, axions. Underground laboratories wait for whispers of interaction. None have spoken. Still, the evidence mounts: gravitational lensing, cosmic microwave echoes, galactic rotation curves. All point to an invisible architecture upon which the visible universe is built. But some rebel, modified gravity theories offer alternatives, subtle tweaks to Newton and Einstein that might explain the data without invoking hidden mass. Yet the consensus holds dark matter is real. We just haven't seen it. So we are left with maps of shadows, scaffolds of mystery, and equations filled with unknowns. The universe, it seems, is not just vast, it is veiled. And yet, in every black hole's silence and in every unseen mass that bends starlight, we hear an echo of something ancient and unfinished. The cosmos is not just out there. It is also within, woven into our atoms, mirrored in our questions, and reflected in the quiet hunger that drives us to look up and ask, what else lies beyond? The deeper we peer into the cosmos, the more the fabric of reality seems to stretch under our gaze, not in the literal sense of expansion, though that too continues without pause, but in the way our understanding is constantly reshaped by the very act of observation. Nothing illustrates this better than the nature of time itself. Time, as we experience it, flowing, irreversible, consistent, is not a universal constant. On Earth, it behaves predictably enough for clocks and calendars to order our lives. But across the curved architecture of space-time, time can stretch, slow, or even fracture, depending on speed and gravity. According to Einstein's theory of general relativity, time is not an arrow but a dimension, one that can warp and bend like any other. Near the event horizon of a black hole, a clock slows almost to a halt. From the perspective of an outside observer, fall too close, and your seconds become centuries to someone watching from afar. To you, the fall is brief. To the universe, you have been suspended at the edge of eternity. This warping isn't poetic metaphor. It's been observed, measured. GPS satellites orbiting Earth must adjust for the time dilation caused by both their velocity and their altitude. Without accounting for relativity, your navigation system would be lost. Such effects hint at a deeper truth: time is not absolute. And in the quantum realm, time becomes even stranger. At small scales, particles do not obey strict sequences of cause and effect. Events can be entangled across time, influencing outcomes in ways that challenge our everyday intuitions. In some interpretations of quantum mechanics, the future can shape the past. In others, time is not fundamental at all, but emerges from patterns of correlation. As we probe deeper into quantum gravity, new ideas emerge. One proposes that space-time is not continuous, but discrete, a kind of quantum fabric woven from tiny loops or strings. Another suggests that space-time itself is a hologram, with three-dimensional space and one-dimensional time projected from lower dimensions. These are not just wild guesses. They are mathematically rigorous theories under active investigation, awaiting experimental support. Beyond the scientific implications, there is something profoundly human about this search. We do not only want to know what time is, we want to know what it means. Why does it feel the way it does? Why does the past feel fixed, the future uncertain, the present fleeting? Are these feelings illusions, side effects of entropy and cognition, or do they reveal something deeper about our relationship to the cosmos? Entropy, the measure of disorder, is the only known physical quantity that gives time a direction. It tells us why we remember the past but not the future, why eggs break but don't unbreak, why stars burn but don't spontaneously reform. As the universe ages, its entropy increases. Structures dissolve, heat diffuses. The arrow of time points toward equilibrium, toward a future of uniformity. And yet, in this entropic drift, complexity arises, galaxies form, stars ignite, life evolves, brains ponder, order emerges locally, temporarily, as the universe flows toward disorder. This paradox that complexity can grow even as entropy rises may be the key to understanding time not just as a physical dimension, but as a narrative thread. When we study the origins of time, we inevitably encounter the origins of memory. To remember is to mark time, to extract meaning from change. Memory is not just a neurological function. It is a survival strategy, a form of low-resolution time travel. It allows us to model cause and effect, to plan, to imagine. In a way, our brains are clocks tuned not just to the world outside, but to the unfolding of our inner universe. Perhaps this is why time fascinates us so deeply. It is not just something we measure, it is something we are, made of star stuff. Yes, but also of sequences and stories, of beginnings and becomings. Every atom in your body was once part of a star. But every thought you have is part of a timeline, a chain of cause and consequence that reaches from the origin of consciousness to the edge of what you can imagine. And as we extend our measurements further beyond galaxies, beyond radiation, into the whispering tremors of gravitational waves, we listen not just to the movements of matter, but to the ripples of time itself. Detectors like LIGO and Virgo, and future ones like LISA, are not just instruments. They are ears pressed to the space-time fabric, waiting to hear what cannot be seen. The universe speaks in more than one language. Light is only one, gravity is another. Particles speak in probabilities, fields in fluctuations. Time, perhaps, speaks in memory, in patterns, in the difference between before and after. And as we learn to listen in all these tongues, we approach something extraordinary, not a final answer, but a deeper resonance, a way of hearing ourselves as part of the unfolding story of the cosmos. High above the dense veils of Earth's atmosphere, orbiting telescopes capture starlight that began its journey long before humanity discovered fire. That ancient light, encoded with stories of formation and fire, glints against the polished lenses of spaceborne observatories like Webb and Hubble. From those gleams, we extract the atmospheres of exoplanets, decipher the elemental alchemy of distant galaxies, and peer however faintly into the birth pangs of the first stars. Among those stars, some live quickly and die young, their ends heralded by magnificent outbursts, supernovae that seed the cosmos with heavy elements. These elements, carbon, oxygen, iron, are forged in stellar cores and disseminated into the interstellar medium like pollen. Eventually, these enriched clouds collapse to form new generations of stars and planets. It is a feedback loop of cosmic fertility. We do not merely live in the universe, we arise from it. We are its recursion. Yet the process of star formation is neither uniform nor guaranteed. Magnetic fields weave invisible barriers within collapsing clouds. Radiation pressure pushes against gravitational collapse. Turbulence seeds structure while also threatening its unraveling. To model this dance is to model the soul of creation. Our simulations improve, but the universe retains its edge of unpredictability. Still, there is structure. We observe galactic disks spinning with stately grace, stars tracing luminous arms across spiral galaxies. In the galactic core, a hidden colossus, a supermassive black hole, often dormant, sometimes awakening to launch jets of matter at near light speed. These central engines sculpt their host galaxies, regulating star formation through feedback processes we are only beginning to grasp. In the vast intergalactic medium, filaments of hydrogen stretch across millions of light years, forming a scaffold, the cosmic web on which galaxies assemble like dew on a spider's threads. This web, shaped by dark matter and illuminated by galaxies, is our most comprehensive view of structure writ large. The scale continues upward. Clusters of galaxies, bound by gravity, swirl in massive halos. Collisions between them generate shockwaves that heat the surrounding plasma to hundreds of millions of degrees, detectable only in X-rays. These cosmic collisions are not just violent, they are creative. They mix elements, trigger new star formation, and amplify magnetic fields. Between the nodes of this web lies a mystery voids, vast expanses of seemingly empty space, low in matter, low in light, and yet crucial. These voids, by contrast, define the shape of the structure. Their emptiness is not absence, but the complement of presence. Zooming inward, we return to planets. From the nebulae enriched by ancient supernovae, rocky worlds condense. Some orbit perilously close to their stars, scorched by heat and radiation. Others lie in the temperate zone, the so-called habitable band where liquid water may persist. Water so simple, so vital, could bridge chemistry and biology. The chemistry is intricate. In planetary atmospheres, ultraviolet radiation from stars splits molecules. Fragments recombine into organics. On some worlds, these reactions may remain suspended in prebiotic loops. On others, they may tip into life self-replicating, evolving, diversifying. We do not yet know how common this transition is, but with each passing year, we catalog more planets, refine our techniques, and move closer to the answer. Some planets exhibit signs of volcanic activity, plate tectonics, or magnetic fields, all crucial for stabilizing climates and recycling nutrients. Others may harbor subsurface oceans beneath icy crusts. On moons like Europa and Enceladus, plumes of water erupt into space, hinting at warm, salty oceans within. To sample these plumes is to sniff the breath of a hidden sea. Our own planet, Earth, reminds us of the fragility and tenacity of life. From extremophiles in deep ocean vents to microbes suspended in the upper atmosphere, life adapts. It thrives in acid, in cold, in radiation. This versatility expands our conception of habitability. Life, it seems, is not an anomaly, but a potential, a latent possibility written into chemistry wherever conditions align. And perhaps intelligence, too, is such a potential. On one world, life evolved neurons, then language, then symbols, then radio waves. We now scan the sky not only for signs of planets, but for patterns, mathematical or musical, that might hint at minds across the void. But if the cosmos is teeming with intelligence, why have we not heard from it? The paradox is sharp. Are we early? Are they hiding, or does intelligence self-destruct before it can connect? The silence is not evidence of emptiness. It is an invitation to listen deeper, to speak more clearly, to search not only with instruments, but with imagination. The search for meaning in the stars ultimately turns inward, beyond instruments and telescopes, beyond the algorithms and the arrays. There is another kind of observatory, the mind. It is within consciousness that the universe loops back upon itself. For we are not outside of nature. Looking in, we are nature looking out. Consciousness is perhaps the greatest mystery of all. It is not enough to know that we think or that we experience. The deeper question is how does matter, organized in just the right configuration, generate awareness neurons, electrical impulses, neurotransmitters. These are the components. But what gives rise to the feeling of being, the internal narrative, the sense of now? Some theories suggest consciousness is an emergent property, a side effect of complexity. Others argue it is fundamental, not reducible to anything else, perhaps even a basic feature of the universe, like mass or charge. Integrated information theory, for instance, proposes that consciousness arises from the degree to which a system integrates information. In that view, a brain is conscious because its parts are interconnected in just the right way. But if consciousness is real and irreducible, it must leave a mark. And it does. Not only in thought, but in culture, in ethics, in science itself. The fact that we can pose questions about the nature of existence, about black holes, dark energy, time, and origins suggests something astonishing. The universe has evolved a way to reflect on itself. In this light, technology is not just an extension of our hands. It is an extension of our minds. Telescopes, particle accelerators, neural networks, they are all instruments of introspection as much as observation. Through them, we translate curiosity into insight. We construct models not only of the cosmos, but of ourselves. Artificial intelligence enters here, not merely as a tool, but as a mirror. As our algorithms learn to model speech, perception, even creativity, we begin to ask new questions. Can a machine be aware? Can consciousness be synthesized? What are the moral contours of a thinking machine? And if intelligence can emerge from silicon as it did from carbon, is life's substrate less important than its architecture? These are not distractions from cosmic inquiry, they are its deepening. For to ask about alien life, we must understand life. To seek intelligence beyond Earth, we must first recognize it in ourselves. And as we build systems that mimic facets of thought, we uncover the scaffolding of our own cognition. Meanwhile, the clock continues. Stars die, galaxies drift, the cosmic horizon recedes. If the universe's expansion continues accelerating, then distant galaxies will vanish from view, their light redshifted into nothingness. One day, even the nearest galaxies will lie beyond reach. In that future, the cosmos becomes parochial, each observer an island in an ocean of darkness. And still we dream, we craft futures that transcend limitation, generation ships that drift between stars, Dyson spheres that capture stellar energy, civilizations that spread through galaxies like seed and fire. We imagine minds embedded in networks, intelligences that endure beyond biology. We conjure futures vast and strange. These dreams are not predictions, they are provocations, thought experiments that stretch our sense of the possible. They remind us that the universe's scale is matched only by the scale of imagination. And perhaps, that imagination is the most powerful force we possess. For even now, we are reshaping Earth, not just its surface, but its atmosphere, its climate, its future. We are agents of planetary change. That power comes with cost. The Anthropocene, this human epoch, demands reckoning. As we master forces once the province of stars, we must wield them with care. The fate of Earth is not separate from the fate of the cosmos. What we do here ripples outward. Our choices etch themselves into the geological record. Our satellites encircle the planet like metal moons. Our digital archives may outlast cities. And so, the final frontier may not be space, but responsibility, to become stewards of our world, to ensure that intelligence endures not by conquering, but by conserving, not by escaping, but by understanding. In that understanding lies hope, not a naive optimism, but a grounded commitment to continuity, to legacy, to the long view, because even as the stars drift apart and the universe grows cold, a trace remains, a whisper, a record that once, in a small corner of space-time, atoms danced in just the right way to become aware, to wonder, to reach, to remember. Long after the last star flickers and fades, when the galaxies have receded into invisibility and the universe settles into darkness, there may still be time, not time as we know it, marked by suns and seasons, but deep time, a cosmic beat measured in trillions of years, a rhythm that continues even in silence. In this far future universe, entropy reaches its apex. Black holes, once the great devourers, evaporate through Hawking radiation. Their final whispers disperse energy into the void. Matter decays. Structures dissolve. What remains is a thin bath of low-energy particles and the fading memory of form. Yet even this ending is not truly final. Some theorists speak of quantum tunneling events, fluctuations in the vacuum that might spawn new universes. Others imagine a cyclic cosmos, where collapse begets rebirth. And still others consider the multiverse a boundless ensemble of realities, each with its own laws, constants, and possibilities. Whether or not such scenarios come to pass, they point to a profound truth. The universe is not static. It evolves, experiments, iterates. It is not merely a space, but a process. And within that process, life brief, luminous has arisen at least once, perhaps many times, perhaps everywhere. The story of the universe is not merely a chronicle of expansion. It is a journey from simplicity to complexity, from plasma to planets, from atoms to awareness, from randomness to reflection. We are the outcome of countless transformations. We are the improbable becoming real. And perhaps we are not the final word. If humanity survives its adolescence, its wars, its climate crises, its existential risks, then it may seed intelligence far beyond its cradle. It may become not a single species, but a symphony of post-biological minds, hybrid forms, digital beings, and conscious collectives. It may give rise to civilizations that write their own laws of physics through technological mastery. Or it may perish, leaving behind a fossil trace, a geologic sigh, a whisper embedded in the isotopes of ancient rock. But for now, we remain on this blue sphere, orbiting a quiet star, flanked by a moon that stirs our tides and our myths. We remain with telescopes pointed outward and instruments tuned to the deep frequencies of space. We ask, we listen, we build, and as we do, we are also building stories, shared narratives that shape how we live and why we strive. Stories of origin, of connection, of future. These narratives matter. They are not merely fictions. They are cognitive architectures, frames through which we organize action, emotion, and purpose. One such frame is stewardship. Another is exploration. A third is synthesis, the integration of knowledge across scales, disciplines, and cultures. In this synthesis, science and art converge. Philosophy informs physics. Biology meets computation. The local touches the cosmic. This is the moment we inhabit, not a final frontier, but an interstitial one, a hinge point between ignorance and insight, between isolation and interconnection. The decisions we make now about energy, governance, equity, curiosity resonate across timescales far beyond our own. So we must think like ancestors. We must act not only for ourselves, but for the descendants we will never meet. We must imagine futures that outlive empires and outshine suns. And we must do so with humility, for the universe is vast, but our knowledge is narrow. Our models are provisional. Our truths are contingent. Yet in that humility is a kind of strength, the willingness to revise, to adapt, to grow. We once looked at the stars and saw gods. Then we saw machines. Now we see data, curvature, probability fields. But perhaps the most important thing we see is possibility. The cosmos is not cold, it is unfinished. And so we continue, not to dominate, but to discover, not to transcend nature, but to deepen our belonging within it. The universe is not elsewhere, it is here, in our breath, in our questions, in the spaces between molecules and galaxies. It is in the silence and in the voice that breaks it, asking, what next? That question, unanswerable and essential, is the signature of intelligence, the evidence that awareness once bloomed in the dark, that, at least once, the universe awakened.
Somewhere beyond the sweep of our immediate solar neighborhood, the Milky Way reveals itself not as a silent arc of stars across the night sky, but as a sprawling system with intricate architecture and hidden depths. 100,000 light-years wide, this galaxy is a continent of stars suspended in a void, its center veiled behind curtains of dust in the direction of the constellation Sagittarius. Light itself, the fastest known messenger in the universe, would take a full 100 millennia to cross its breadth. And yet, in all that vastness, our own sun is just a minor player, situated about 30,000 light-years from the galactic center, orbiting it with measured grace every 200 million years. The Milky Way's visible body is a disk, but this disk is more than a flattened spiral of stars. It is a living, rotating structure, dense with interstellar gas and flecks of microscopic dust that veil and reveal depending on the observer's vantage point. Embedded in this disk is over half the galaxy's observable mass stars of varying ages and chemistries, gas clouds primed for stellar birth, and fragments of dust forged from long-dead stars. Only about 1% of this matter consists of dust, yet that sliver plays a disproportionate role in shaping what we can and cannot see. These dust grains, smaller than a micron, are the ashes of stellar cycles, riding the galactic winds and gathering in the cold nurseries where new stars begin to shine. The Sun, a population one star born from gas already seeded with heavy elements, is one of many in this enriched region of the disk. Unlike its older cousins in the halo, it formed from gas that had witnessed previous generations of stellar death and rebirth. These earlier stars forged elements heavier than helium-carbon, oxygen, silicon, iron, and dispersed them into space. Over time, these materials coalesced into dust grains, then into meteoroids, and eventually into planets. It's from this lineage that Earth itself was born, a world possible only in a galaxy old enough to recycle itself. Circling this luminous disk like a ghostly shroud is the galactic halo, an enormous, faintly populated region stretching nearly 200,000 light-years across. It is not symmetrical or vibrant like the disk. Instead, it is sparse and ancient, a graveyard of primordial stars. The halo does not rotate in concert with the disk. Its stars drift in elliptical orbits, indifferent to the ordered dance below. These are population 2 stars old, metal poor, relics from a time before galaxies had matured. Many are gathered into globular clusters, each a self-contained sphere of hundreds of thousands of stars, all born together over 8 to 15 billion years ago. In these stars, the periodic table ends early. With virtually no heavy elements, their chemistry would not permit the formation of complex planetary systems. In a very real sense, they are orphans of cosmic evolution formed too early, from too little, in an era before stars could build the ingredients for worlds. If intelligent life is to exist, it would almost certainly favor the newer stars, the ones born from richer materials, in denser and more dynamic parts of the galaxy. Between the disk and the halo lies a transitional zone, the nuclear bulge. This central sphere is a gravitational furnace of stellar activity, where population 1 and 2 stars intermingle. The region is so crowded that stars lie hundreds of times closer to each other than in our corner of the galaxy. Dense gas flows here in eddies and spirals, and embedded within this chaos, perhaps hidden beneath the glare of surrounding matter, are the suspected giants, supermassive black holes whose gravitational appetites drive the complex energy dynamics of the core. Star clusters offer a way to measure the distances that separate these structures. Open clusters, loosely bound groups of young stars dot the disk and often cling to their birth clouds for a few million years. The Pleiades and Hyades clusters are close enough for astronomers to calculate their distances through parallax and Doppler-based methods. Globular clusters, on the other hand, are scattered mostly in the halo and nuclear bulge, with precise alignments that allow scientists to calibrate distance scales using brightness and temperature. The Hyades cluster plays a pivotal role in this cosmic cartography. It acts as a yardstick for the galaxy and, by extension, the universe. Through techniques like the moving cluster method and main sequence fitting, its measured distance enables astronomers to leapfrog across space using pulsating Cepheid stars as lighthouses to estimate the distances of remote galaxies. Dust, however, complicates everything. Even the clearest cosmic window is rarely truly transparent. The interstellar medium is thick with particles that obscure, absorb, and scatter starlight. Like fog dimming the view across a field, these clouds can reduce a star's brightness to a fraction of its intrinsic glow. Every 3,000 light-years through the disk, the intensity of visible starlight is halved. Beyond 6,000 light-years, the dimming can make stars appear just 1/4 as bright as they would otherwise be, an effect that masks the galaxy's heart from view. Yet this shroud is selectively permeable. Long wavelength light in the infrared and radio ranges pierces through the dust, where optical telescopes see only a void. Instruments tuned to these wavelengths reveal a roiling, star-strewn core. This central bulge, extending 10,000 light-years from the nucleus, is not a featureless void but a labyrinth of stellar birth and death, of collapsing clouds and radiating gas. Multiple sources of strong radiation suggest something formidable lies hidden, perhaps one or more supermassive black holes, concealed not by design, but by dust and distance. As segment 1 fades, it leaves behind a vision of the Milky Way not as a static map of star positions, but as a dynamic arena of birth and memory, structure and entropy. From the ordered orbits of population 1 stars to the drifting remnants in the halo, this first layer of our galactic understanding sets the stage for deeper questions about cosmic structure, stellar evolution, and the forces that shape everything from black holes to planetary systems. Turn your gaze outward past the boundary of our galactic halo, beyond the reach of our sun's gravitational leash, and the solitary glow of our Milky Way gives way to a spectacle far grander, a universe laced with galaxies. What once appeared to the human eye as faint, cloudy smudges on telescope plates have been resolved into entire star cities. Each galaxy, in motion and in flux, spins its own narrative of birth, transformation, and decay, set within a vast web of structure that challenges our every cosmological model. These galaxies are not scattered at random, like raindrops on a spiderweb. They stretch across the cosmos in filamentary threads and clustered knots. Some are faint, irregular sparks barely distinguishable from globular clusters. Others, like Andromeda or M87, are monumental, their diameters surpassing 500,000 light-years. Most galaxies fall into recognizable shapes: elliptical, spiral, barred spiral, each category a frozen frame from the universe's dynamic evolution. Elliptical galaxies are the most common, making up over 60% of all known galaxies. Their forms are ovoid, smooth, and largely featureless, from the near-spherical E0s to the more elongated E17s. These systems are the ancient vaults of the universe. They lack spiral arms, possess little gas or dust, and contain mainly population 2 stars, ancient, low-metal stars born when the universe itself was still cooling into complexity. Some are mere dwarfs, only marginally larger than star clusters. Others, like the supergiant M87, are monstrous in scale, containing hundreds of billions of stars and harboring colossal black holes in their cores. These elliptical giants often dominate the gravitational centers of galaxy clusters, growing fat on mergers and cosmic cannibalism. In contrast, spiral galaxies like our own wear their age more flamboyantly, with bright, swirling arms wrapping around dense nuclear bulges. They offer a vivid tableau of ongoing stellar life. Their disks are rich in gas and dust, ideal conditions for star formation, and their arms sparkle with the blue-white intensity of young, short-lived stars. These spiral arms are not static structures, but moving density waves, regions where interstellar gas is compressed just enough to trigger gravitational collapse. Newborn stars blaze briefly before fading, leaving behind clusters and remnants that slowly drift away. The spiral arms' longevity presents a paradox. If stars and gas rotated within them as solid features, they would wind tighter and tighter over time, contradicting the loose pattern seen in even the oldest galaxies. This winding problem found its solution in Bertil Lindblad's density wave theory. The arms are not collections of fixed stars, but are more like traffic jams, ripples in space density through which stars and gas pass. This ripple triggers waves of star formation without requiring a rigid structure. The luminous arms are ephemeral, lit by stars that will soon burn out or drift away. But the underlying wave pattern persists, like music played across cosmic time. Galaxies aren't static islands. They belong to groups, clusters, and superclusters. Gravitational associations on scales so immense they defy everyday experience. Our Milky Way is a member of the local group, a modest, irregular cluster of around 20 major galaxies. Its most prominent neighbors, the Andromeda Galaxy and the Triangulum Galaxy, are spirals as well, and the gravitational interplay among them is already reshaping the future. Billions of years from now, Andromeda and the Milky Way will collide and coalesce, forming an elliptical galaxy far larger than either progenitor. Beyond the local group lies the Virgo cluster, a clumpy, irregular swarm of galaxies located about 70 million light-years away. Rich clusters like Virgo contain thousands of galaxies, from delicate spirals to hulking ellipticals. They lack the symmetry of globular star clusters, but exert influence across cosmic distances. Even more massive are the so-called regular clusters, like the Coma cluster, which stretch 10 million light-years in diameter and teem with thousands of galaxies bound together by gravity and perhaps even dark matter. These galaxy clusters are not merely gatherings of stars, they are violent arenas. As galaxies plunge through their environments at thousands of kilometers per second, they interact with streams of intergalactic gas. This high-speed motion through dense plasma can strip galaxies of their own gas, halting star formation and transforming them from active spirals into passive lenticulars. These S0 galaxies, once rich with life, now resemble swept-clean versions of spirals disks without the glow, arms without the pulse. The broader architecture of the universe begins to emerge only when we step even further back. Galaxy clusters themselves group into superclusters, forming a foam-like structure, a vast web where filaments of galaxies are separated by voids spanning hundreds of millions of light-years. Our local group resides within the Laniakea supercluster, which is centered near the Virgo cluster. The structure is gravitationally complex, shaped not only by the visible matter we observe, but also by a scaffolding of dark matter that tethers galaxies into these immense patterns. In trying to understand the variety of galaxies, astronomers have long sought a taxonomy. The most iconic is Edwin Hubble's tuning fork diagram. On one side lie elliptical galaxies, from nearly round E0s to elongated E7s. At the junction are S0 galaxies disk-shaped but gas-poor. From there, the diagram forks into two branches, normal spirals and barred spirals, categorized by the size of their central bulges and the tightness of their arms. Though it was once thought that this diagram reflected evolutionary paths, with galaxies morphing from left to right, or vice versa, modern consensus suggests otherwise. A galaxy's form may be more a matter of birth conditions, density, rotation, and local environment than any smooth transformation over time. But not all galaxies fit the mold. A significant fraction, around 10%, are irregular, defying neat classification. Some are the victims of tidal interactions or galactic collisions. Others are simply primordial systems, never having enough mass to settle into an ordered shape. The small and large Magellanic Clouds, visible in the southern hemisphere's skies, are examples of such irregular galaxies nearby neighbors with chaotic structures shaped by gravitational wrestling with the Milky Way. Here, at the boundary between order and chaos, the story of galaxies becomes one of tension between environment and destiny. Some galaxies are born quiet and remain so, coasting through cosmic time with little disruption. Others are pulled into violent mergers, flung across clusters, or devoured by their larger companions. Yet through all these upheavals, they follow unseen laws, gravity, thermodynamics, and the slow whisper of dark energy stretching the universe like a breathing lung. As we look deeper into space, we also look further into the past. The light from a galaxy 10 billion light-years away left its source when the universe was a fraction of its current age. In that light, we read stories not just of distant structures, but of our own origins. Every distant galaxy is a time capsule, preserving the physics and conditions of an earlier epoch. They hint at a time when galaxies were smaller, more chaotic, and far more prone to rapid star formation. As this segment closes, we find ourselves surrounded by patterns writ large across space, spiral arms and elliptical swarms, dwarf irregulars and giant clusters, all dancing to a rhythm we are just beginning to hear. The universe, once thought to be a scattering of stars, now reveals itself as a carefully choreographed network of galaxies, each a glowing node in a cosmic tapestry. There was a time long before Earth had oceans, long before the sun ignited when galaxies themselves did not yet exist. No elegant spirals or luminous bulges, no clusters or superclusters to carve patterns across the sky. Instead, there was only gas, a uniform expanse of hydrogen and helium, cooling in the aftermath of the Big Bang, expanding like breath into cold air. But even this early universe, seemingly simple, bore within it tiny imperfections, minute differences in density that would become the seeds of all structure. These primordial variations, less than 1 part in 100,000, were not errors but blueprints. Over eons, gravity acted on them, nudging denser regions to grow denser still. As the universe expanded, the average density of matter decreased, but those slightly overdense regions, protuberances in an otherwise smooth fabric, resisted the thinning. Their relative density increased until, at some critical threshold, they began to collapse. From these gentle perturbations, proto-galaxies were born. A proto-galaxy was not a single object, but a region often hundreds of thousands of light-years across where gas slowed, halted its outward drift, and began to fall inward. This gas, still composed mostly of hydrogen and helium forged in the Big Bang, was cool and diffuse. Its fate depended on 3 crucial factors: its mass, its initial rotation, and its internal irregularities. In regions with higher mass, gravity pulled more strongly. Where there was rotation, centrifugal force pushed back. And in areas of internal clumpiness, collapse occurred unevenly, giving rise to the earliest generation of stars. These first stars, population 2 stars, were born in the densest central regions of proto-galaxies, lacking heavy elements. They were composed almost entirely of primordial gas. Many were massive, burning their nuclear fuel rapidly and dying in violent supernova explosions. In their deaths, they seeded their surroundings with heavier elements: carbon, oxygen, iron, the raw materials from which later stars, planets, and eventually life would form. This chemical alchemy, repeated across millions of such first-generation stars, enriched the collapsing gas clouds with each cycle of death and birth. As the proto-galaxy collapsed further, a striking phenomenon occurred. The stars once formed ceased to participate in the general infall. Each star followed an orbit around the growing center, but unlike gas, it could not dissipate energy through collisions or radiation. It remained suspended in motion, while the gas continued to sink. Over hundreds of millions of years, this differential behavior sculpted the emerging galaxy's structure. The early spherical swarm of stars, the halo, remained a fossil record of this initial collapse, while the infalling gas eventually settled into a rotating disk. Here lies a subtle insight: the stars in the halo, the gas in the disk, and the shape of the galaxy are not independent phenomena. They are chapters in a single gravitational history, unfolding in time. A galaxy's form, spiral or elliptical, reflects the balance of forces at play during its formation. In cases where rotation dominated, gas was able to flatten into a disk, forming spirals rich in ongoing starbirth. In galaxies where collapse outpaced spin, The result was more spherical, a structure that consumed its gas rapidly, leaving behind a population of aging stars and little fuel for the future. Yet the narrative does not stop with formation. These early galaxies already differentiated in shape and content, interacted, merged, and evolved. Some spirals collided and formed ellipticals. Some dwarf galaxies were cannibalized by larger hosts. Some retained their integrity for billions of years, like cosmic islands drifting in a sea of expansion. But at the heart of all these changes lay one common force: gravity, ever at work sculpting structure from chaos. Consider a proto-galactic cloud with moderate rotation. As its outer gas collapses inward, the increasing spin creates a barrier. Centrifugal force flattens the flow into a disk. The central region, less affected by this force, becomes a halo. Here, population 2 stars light up first, followed by generations of increasingly metal-rich stars in the disk. Magnetic fields, turbulence, and stellar winds complicate this picture, impeding or delaying star formation. But over time, a majestic spiral emerges, its arms cradling newborn stars, its halo preserving echoes of a forgotten past. Now imagine another scenario: the same cloud, but with higher density and less spin. Collapse occurs more quickly and more uniformly. The gas doesn't have time to settle into a disk. Instead, it feeds an orgy of rapid star formation. With little rotation to resist infall, the gas is consumed before it can spread out. The result: an elliptical galaxy, dense, old, and quiet. Star formation ends early, and the structure remains largely unchanged for billions of years. This dichotomy, disk versus spheroid, spiral versus elliptical, underlies much of modern galaxy classification. But nature, as always, permits exceptions. Intermediate forms emerge. Galaxies with moderate rotation but clumpy collapse may form lenticular shapes. Those with strong initial density variations may fragment into multiple components. And some, battered by collisions or gravitational tides, bear little resemblance to either category, becoming irregular or peculiar in appearance. The process of galaxy formation also invites a broader philosophical contemplation. These structures, vast beyond comprehension, arise not from divine intervention or miraculous design, but from the slow, inexorable unfolding of simple laws. The same equations that govern falling apples and orbiting moons shape the birth of galaxies. Yet from these laws, an astonishing complexity emerges: order, symmetry, beauty. In contemplating the origin of galaxies, we are drawn into a meditation on emergence, how simplicity breeds structure, how chaos gives rise to form. And what of time to us? Galaxies seem eternal, their shapes unchanging across the millennia. But this is an illusion born of scale. Galaxies live, evolve, and die. They merge, shift, and bleed their energies into space. Some lose their gas to intergalactic winds, others collapse into active nuclei. A galaxy that once blazed with newborn stars may one day become a ghost, its brilliance faded, its arms smudged into obscurity. Seen in this light, galaxies become more than astrophysical phenomena. They are timelines, each one recording a different version of cosmic history. Some tell of quiet births and long, graceful evolutions. Others are chronicles of violence, of mergers, collisions, and sudden transformations. And embedded within each is the memory of conditions from a time when the universe was young, denser, and hotter. The current distribution of galaxy types, then, is not arbitrary. It reflects the timing of their formation, the initial conditions of the expanding universe, and the complex choreography of matter under gravity. Fragmentation and aggregation, these two principles, once thought opposed, now appear as partners in a universal dance. From tiny fluctuations in density came the building blocks of structure. From collapsing globes came stars. From the clustering of galaxies came superclusters. And from them, the vast, luminous web that defines our cosmic environment. The very idea that a region with only one hydrogen atom per cubic centimeter, a vacuum by terrestrial standards, could give rise to such richness speaks to the astonishing scale of cosmic processes. What seems empty to us is, on galactic scales, a sea of possibility. What begins as a whisper of imbalance becomes, through time and gravity, a voice shouting across the ages in the form of stars, clusters, and galaxies. In the next arc of our story, we will dive inward again, not into space, but into energy. We will examine what happens when gravity, unopposed, ignites not just stars, but entire galactic cores, turning galaxies into lighthouses visible across the universe, and revealing the monstrous hearts that dwell within. Somewhere in the depths of a galaxy, not in the quiet outskirts where stars drift serenely, but in the violent central furnace where matter crushes into itself, a singular hunger awakens. This is not a star, nor even a cluster of stars. It is a presence invisible, insatiable, and capable of swallowing light itself. At the core of many galaxies, including our own, lies a black hole, not just any black hole, but a supermassive one, containing millions or even billions of solar masses compressed into a volume scarcely larger than our solar system. To encounter such an entity is to brush against the limits of what physics can describe. A black hole is not a thing so much as a region of altered reality, where gravity warps space and time to extremes. But it is not the black hole alone that makes a galaxy's center luminous. Paradoxically, it is what surrounds it, gas spiraling inward, forming a blazing accretion disk heated to millions of degrees that transforms these invisible monsters into some of the brightest objects in the universe. These blazing hearts are what we now call active galactic nuclei, and when they flare to their fullest intensity, we see them as quasars, quasi-stellar radio sources. Though not all are loud in radio, from billions of light years away, they send us signals, not voices, but pulses of energy so vast that for a time, they outshine entire galaxies. They vary in brightness from week to week, sometimes day to day, which means their engines must be astonishingly compact, smaller than the distance from the Sun to Pluto, yet releasing energy equivalent to hundreds of millions of suns. The analogy is often made between quasars and cosmic lighthouses, but that metaphor understates the violence. These are furnaces of annihilation, converting matter into energy with efficiencies unmatched by any known process short of total nuclear conversion. As gas falls into a black hole's accretion disk, it accelerates, collides, compresses, and heats. Magnetic fields twist and snap. Particles reach energies that dwarf anything our machines can achieve. The process is chaotic, yet strangely efficient. Perhaps 10% of the infalling matter's mass is transformed into radiant energy, released across the electromagnetic spectrum. And not all of that energy radiates passively. Some of it is funneled into jets, collimated beams of plasma that shoot from the poles of the accretion disk at near-light speeds, stretching hundreds of thousands of light years into intergalactic space. These jets carve tunnels through the surrounding medium, lighting up radio lobes that balloon like smoke rings around the host galaxy. From Earth, we see them as two lobes of radio emission, straddling a galaxy too distant to resolve, like twin searchlights from some forgotten war. The mechanisms behind these jets are still not fully understood. Some theories invoke magnetohydrodynamics, the same physics that governs sunspots and solar flares, magnified a billionfold. Others suggest that the rotation of the black hole itself, the so-called Kerr metric, twists spacetime, dragging magnetic field lines and launching particles outward. Whatever the cause, the result is spectacular radiation bursts that can last millions of years, shaping the galaxy's evolution and influencing its neighbors. Yet quasars do not burn forever. They flare, shine, and fade. When their fuel runs low, when the surrounding gas has been consumed, blown away by radiation pressure, or ejected by gravitational feedback, they fall silent. The accretion disk dissipates. The jets vanish. The black hole remains, quiet and cold, unless fresh gas stirs it awake once more. The transient nature of quasars suggests that most, perhaps all, large galaxies host supermassive black holes at their cores, and that those black holes go through active phases when conditions permit. In spiral galaxies like our own, the central black hole is often dormant or only modestly active. But in ellipticals, particularly those in crowded galactic clusters, activity can surge. This raises provocative questions. What governs a black hole's feeding schedule? What wakes it? What puts it to sleep? The relationship between a galaxy and its central black hole is not one-directional. While it was once thought that black holes were mere byproducts of galactic evolution, evidence now suggests a deeper interdependence. The mass of a galaxy's bulge correlates tightly with the mass of its central black hole, implying that they co-evolve. Radiation and outflows from active nuclei can regulate star formation by heating or expelling gas. Feedback, in this context, is not a metaphor. It is a literal, energetic coupling between a galaxy's heart and its extended structure. To probe this relationship further is to confront one of the most fascinating frontiers in modern cosmology. Why do galaxies with larger bulges have larger black holes? Does the growth of one limit the other? And what mechanisms ensure this cosmic tuning? Across billions of years and light years, the balance suggests a form of regulation, self-limiting growth, perhaps driven by the same physics that governs planetary atmospheres or ecological systems. In exploring these dynamics, we glimpse a universe where matter behaves like memory. Gas clouds remember the energy they've absorbed. Stars remember the metals forged by earlier generations. Black holes remember every photon they've consumed, storing mass without revealing it. And galaxies, as structures, remember their origins through the quiet echoes of their most violent epochs. But the significance of quasars, AGN, and black holes extends beyond astrophysics. They challenge our philosophical frameworks. Here are entities that cannot be seen directly, yet whose influence is undeniable. They remind us that reality is not limited to the visible, that the most powerful forces in nature are often cloaked in shadow. They are monuments to the limits of our perception and invitations to stretch those limits further. Imagine standing on a planet orbiting a star that once belonged to a quasar-hosting galaxy. In its sky, there might have been a time when night was not dark, when the galactic core blazed like a second sun. The spectacle would have lasted for epochs, longer than civilizations. And then, as quietly as it began, the light would fade. The black hole would remain, silent and unremarkable, as though the fire had never been. These cosmic flickers remind us of transience at scales we rarely consider. They are not just lights in the sky, but chapters in a story of becoming birth, hunger, radiance, decline. They are galactic myths, written in X-rays and radio waves, whispered across billions of years. In the next and final arc of our journey, we will follow these whispers outward beyond galaxies and clusters, into the web of the cosmos itself. We will trace the structures that galaxies form, and explore the frontier where cosmology meets origin, how the universe gave rise not just to stars and black holes, but to the framework of space-time we call reality. The sky above, so apparently empty, is a structure of astonishing complexity. Through the lens of modern astronomy, the cosmos reveals itself not as a scattering of isolated galaxies drifting in random solitude, but as an immense, interconnected web of filigree of matter that stretches across the observable universe, shaped by forces rooted in the earliest instants of time. Clusters of galaxies, each containing thousands of constituent systems, gather into even larger conglomerates, superclusters, bound loosely by gravity and connected by vast filaments of gas and dark matter. These filaments span hundreds of millions of light years, woven together like the threads of an invisible lattice. Between them are cosmic voids, enormous regions of near-nothingness, where only a few galaxies reside. It is this cosmic web that frames the large-scale structure of the universe. Our own local group, a modest collection of about 30 galaxies, including the Milky Way and Andromeda, belongs to the Virgo supercluster, which in turn is part of a still grander structure known as Laniakea, a name that means immeasurable heaven in Hawaiian. But these designations, however poetic, fail to convey the scale. The Virgo supercluster alone spans over 100 million light-years, yet even it is just one among many. As we peer farther into space, we look deeper into time. Light from the most distant galaxies began its journey billions of years ago, when the universe was young and galaxies were more primitive, compact, and chaotically formed. These early structures were shaped by gravity acting on minuscule ripples in the density of matter fluctuations born during the first fractions of a second after the Big Bang. It is within these fluctuations that the seeds of all structure were sown. To understand how galaxies emerged from this primordial soup is to confront a sequence of delicate thresholds. When the universe was just a few 100,000 years old, it cooled enough for protons and electrons to combine into hydrogen atoms. This recombination rendered the universe transparent, allowing light to move freely. We observe this light today as the cosmic microwave background, a faint, uniform glow that fills the sky in every direction. But that calm was deceptive. Underneath the uniformity were those subtle variations, places where matter was slightly more dense. Over billions of years, gravity amplified those imperfections. Matter clumped, gas cooled, and stars ignited. Protogalaxies formed, collapsed, and merged. In some regions, immense concentrations of matter became the cradles of galaxy clusters. In others, matter flowed outward, leaving voids behind. The universe sculpted itself through a dance of attraction and expansion. The competing influences of gravity and dark energy define this process. Gravity pulls matter together, forging structure. Dark energy, the mysterious force accelerating the expansion of space, acts in opposition, driving galaxies apart. Their interplay has defined the universe's evolution since its earliest epoch. At present, dark energy dominates. Galaxies not bound in clusters are receding from one another at ever-increasing speeds. Their light redshifted into invisibility. This cosmic acceleration means that some galaxies we now observe will, in time, vanish from view altogether. Beyond a certain horizon, the so-called cosmic event horizon light emitted today will never reach us. It is not that the galaxies are moving faster than light, but that the space between us and them is stretching too quickly. To observe the universe, then, is also to witness a kind of slow disappearance, a graceful, irreversible fading. And so the cosmos becomes a narrative about presence and absence, about what can be seen and what is forever out of reach. It is a theater of becoming and forgetting. Each star that dies, each galaxy that recedes, each quasar that dims, adds to the silent memory inscribed across space-time. In this context, even the vastest structures become ephemeral. Superclusters are not gravitationally bound holes. Over unimaginable time spans, they too will dissolve. The cosmic web will stretch into filamentary remnants. Clusters will become isolated archipelagos. Eventually, star formation will cease. The brightest lights will burn out, and black holes will dominate the scenery, slowly evaporating, particle by particle, in the cold abyss. This far future is not grim, but profound. It is not the absence of purpose, but the ultimate expression of transformation. The cosmos, from its birth in a flash of light to its slow fade into entropy, is an unfolding of possibility. That it gave rise to galaxies, to stars, to life, and to minds that ask these questions is a reflection not just of physical law, but of contingency, emergence, and wonder. And, even here, among collapsing globes of gas and retreating horizons, new questions bloom. Could there be other universes beyond our own observable edge? Might the inflation that seeded our cosmos have birthed others, each with their own laws, their own physics, their own time? The multiverse, once a speculative idea, is now a serious proposition in cosmological circles. Some theories suggest that universes bubble into being like foam, each expanding into its own pocket of space-time. Others propose cycles, cosmic rebirths through black holes, bounces, or emergent quantum geometries. In these models, our cosmos is not the only story, but a page in a larger anthology. We do not yet know if these ideas are testable, but they serve a vital role. They remind us that explanations always open into further questions, that knowledge is not an end, but a pathway. Perhaps that is the deepest lesson of the universe. Its immensity is not designed to dwarf us, but to awaken us, to consider galaxies not merely as objects, but as relationships between matter and light, between energy and curvature, between chaos and order, is to realize that the universe is not something apart from us. We are its outcome and its witness. From the spiral arms of our galaxy to the collapsing cores of protogalaxies, from the dust between the stars to the jets of quasar light that travel for eons, we are entangled in this structure, composed of its remnants and guided by its patterns. To know it is to recognize that the cosmos is not merely a place, but a process, and that we, fleeting and fragile, are part of its unfolding. In that sense, the sky is not silent. It speaks through gravity, through photons, through the whisper of hydrogen and the flare of collapsing stars. All we need is to learn to listen.
In a remote galaxy billions of light years away, a star 100 times more massive than our sun is dying. For a brief moment, it will unleash more energy than 1 trillion suns combined, sending shockwaves across space-time itself. The light from that explosion, a messenger carrying tales of cosmic violence, began its journey when Earth was still a molten world, a formless sphere of rock and fire. That light is now arriving, painting our telescopes with the final, brilliant act of a stellar giant. We perceive it as an event happening tonight. Yet the star itself has been a black hole or a scattered cloud of dust for eons. This delay, this gap between an event and its observation, is not a mere inconvenience. It is a fundamental law of the cosmos, a barrier that separates what is from what we can know. The universe is not a static picture we view through a window. It is a story told in echoes, and the narrator is light, a traveler bound by an absolute speed limit. That limit, 186,000 miles per second, is both our connection to the cosmos and our ultimate prison. It means the farther we look into space, the deeper we look into time. Seeing galaxies as they were when the universe was younger, smaller, and more turbulent. The starlight that reaches us from the Andromeda galaxy, our nearest major neighbor, departed 2.5 million years ago. Beings on a planet in that galaxy, looking toward the Milky Way, would not see our civilization, our cities, or our satellites. They would see a sky where Earth is inhabited by early hominids, still millions of years away from forging tools or questioning the stars. Our present remains invisible to them, just as their present is a secret kept from us, locked behind a 2.5 million year wall of time. This cosmic horizon, the edge of what we can possibly see, is not a physical wall but a boundary of information. Beyond it lies a universe we can theorize about but never directly observe. Light from those unimaginably distant regions has not had enough time to reach us since the beginning of everything. 13.8 billion years ago, the universe might be infinite, stretching on forever with countless other galaxies, stars, and perhaps even other forms of life. But our knowledge is confined to a finite bubble, a sphere of observation with Earth at its center. Every direction we look, we see the past, and at the ultimate edge of that vision lies the faint, lingering glow of the universe's birth. This wall of light, the cosmic microwave background, is the oldest photograph we will ever possess. A baby picture of the cosmos when it was just 380,000 years old. It is a relic of a time when the universe was a hot, dense fog. Before the first stars ignited, before the first galaxies coalesced. It is the echo of creation, a whisper that fills all of space, carrying the seeds of everything that would ever exist. This boundary defines our reality, a testament to the fact that we are participants in a cosmic story that began long before we arrived and will continue long after we are gone. We are latecomers to a drama of unimaginable scale, piecing together its plot from the ancient light that falls upon our world. Deep inside every atom in your body, an invisible war is raging. Protons packed together in the nucleus should tear themselves apart instantly. Their positive charges repel each other with tremendous force, like trying to push two powerful magnets together. Yet somehow they remain locked in place by the strongest force in the universe. The strong nuclear force operates at distances smaller than a single proton, but its power is absolute. Scientists measure it as 100 times stronger than electromagnetism and 100 trillion times stronger than gravity. If gravity were a whisper, the strong force would be a thunderclap that could shatter mountains. This force, the silent guardian of matter, is what allows existence as we know it. Without it, the universe would be a thin, uniform soup of hydrogen. A sea of lonely protons and electrons with no complexity, no stars, no planets, and no life. It is the architect of structure, the power that forges the elements in the hearts of stars and holds them together against the immense pressure and heat. Its very nature is a paradox of scale, a force of unimaginable might that operates only across the most infinitesimal distances. It is the titan in the atom, the power that builds worlds, one nucleus at a time. This force works through particles called gluons, which act like invisible chains, binding quarks together to form protons and neutrons. The more you try to pull these fundamental particles apart, the stronger the force becomes. It is like stretching a rubber band that grows thicker and more resistant with every inch you pull. This bizarre behavior, called confinement, means you can never isolate a single quark, no matter how much energy you apply. When you try to separate quarks, the energy you add simply creates new quarks and gluons, like trying to cut a chain only to have it grow new links. Inside each proton, 3 quarks dance in a prison of pure energy, a web of interactions so complex that even our most powerful supercomputers struggle to model it. This quantum prison is the foundation of all matter. It ensures that the building blocks of the universe remain stable, that protons do not decay into a spray of more fundamental particles, that the very substance of our reality holds together. This force shapes the very building blocks of matter. It determines which atomic nuclei can exist and which cannot. It sets the rate at which stars burn their nuclear fuel, a cosmic thermostat that dictates the lifetimes of suns. It controls the balance between creation and destruction in the hearts of every star across the cosmic void. Yet despite its incredible power, the strong force has a fatal weakness. Its reach extends only to the edge of an atomic nucleus, about 1/10,000,000th the width of a human hair. Beyond that microscopic realm, its influence vanishes completely, and other powers take control. It is a giant confined to a subatomic cage, a king whose absolute authority ends at the palace gates. Our spacecraft engines ignite with the power of 1,000 suns as we break free from Earth's gravitational embrace. The blue marble that has been humanity's home for millions of years shrinks to a pale dot behind us, then disappears entirely into the cosmic darkness. We are now truly alone in the void, beginning the longest journey any conscious being has ever attempted. The first challenge hits us immediately: the sheer scale of what we are attempting. To reach Andromeda, we must travel a distance so vast that light itself, moving at 186,000 miles per second, takes 2.5 million years to make this journey. If we could drive there in a car at highway speeds, never stopping, never sleeping, it would take us 30 billion years. But we have technology beyond current human imagination. Our vessel bends space and time around itself, creating a bubble of warped reality that allows us to slip between the normal rules of physics. We accelerate not through space, but through the fabric of space-time itself. The stars around us begin to shift and blur as we approach speeds that would have been impossible just moments before. This is the only way to traverse the void, not by conquering distance, but by redefining it. By treating the universe not as a space to be crossed, but as a tapestry to be folded. The journey is not just a physical one, it is a conceptual one. A shift in understanding how reality itself is constructed. As we leave our solar system behind, we pass through the Kuiper Belt, where ancient chunks of ice and rock drift in eternal darkness. These are the leftover building blocks of our solar system, frozen in time for 4.5 billion years. Pluto, once considered our 9th planet, appears as a lonely sentinel guarding the edge of everything we have ever known. It is a world of nitrogen glaciers and mountains of water ice, a testament to the cold, slow processes that shape the outer reaches of a star's influence. Beyond Pluto lies the Oort cloud, a spherical shell of icy objects that extends nearly a light year from our sun. This is where comets are born, in the frigid depths where temperatures drop to just a few degrees above absolute zero. We are entering a region where the sun's influence barely reaches, where the space between objects is so vast that collision is nearly impossible. The nearest star to our sun, Proxima Centauri, glows like a red ember in the distance. It would take conventional spacecraft over 70,000 years to reach it. But we pass it in what feels like minutes. We are now in interstellar space, the vast emptiness between star systems, where matter is so sparse that you could travel for millions of miles without encountering a single atom. This is where most space travelers would feel the crushing weight of isolation. But we push forward with purpose. The Andromeda Galaxy beckons from across the cosmic ocean, its spiral arms slowly rotating in a dance that has continued for billions of years. We are no longer bound by the limitations of our species or our world. We are explorers of the infinite. The very concept of a journey on this scale forces a reevaluation of time. The 2.5 million years it takes light to cross the gulf between our galaxies is a period longer than the existence of our own species. Civilizations could rise and fall in the time it takes for a single photon to complete its voyage. The universe operates on timescales that make human history seem like the briefest flicker of a candle in a storm. Our technology, which folds space-time to make this journey possible, does not conquer time itself. It merely creates a pocket of local time, a bubble of distorted physics where our clocks tick at a different rate from the universe outside. For us, the journey may take years, but for the cosmos, millions of years will have passed. We will arrive in a future we can only guess at, a galaxy that has aged and evolved in ways we cannot predict. This temporal dislocation is the true price of cosmic travel. We are not just explorers of space. We are time travelers, adrift in the currents of a river that flows at different speeds in different places. The loneliness of the void is not just about the absence of matter. It is about the separation from a shared moment, a disconnection from the universal clock that governs all things. We are becoming untethered from our own history, an island of consciousness moving through a sea of time. This journey through the void is also a journey through the unseen. We enter the local void, a region of space so empty it defies comprehension. Here, between the galaxy clusters, matter exists in concentrations so low that an entire cubic meter of space might contain only a single atom. The temperature drops to just a few degrees above absolute zero, and the only light comes from distant galaxies billions of light years away. This is cosmic loneliness on a scale that breaks human understanding. If Earth were placed in the center of this void, our night sky would be completely black except for the faint glow of the Milky Way itself. No other galaxies would be visible to the naked eye. Ancient civilizations would have developed entirely different mythologies, religions, and scientific theories about the universe based on this profound isolation. But the void is not truly empty. Dark matter, the mysterious substance that makes up 85% of all matter in the universe, forms invisible scaffolding throughout this region. We cannot see it directly, but its gravitational influence shapes the very fabric of space-time around us. Our instruments detect its presence through subtle variations in the cosmic microwave background radiation, the afterglow of the Big Bang itself. It is the ghost in the machine, the silent architect of cosmic structure, holding galaxies together and guiding their dance across billions of years. As we travel deeper into the void, we encounter something unexpected: rogue planets, ejected from their home solar systems by gravitational interactions with passing stars. These orphaned worlds drift through the darkness, no longer warmed by any sun, their surfaces frozen solid, and their atmospheres collapsed into ice. One rogue planet we encounter tells a particularly haunting story. Its surface shows evidence of ancient oceans kilometers thick. Beneath that ice, our scanners detect something remarkable: a subsurface ocean, kept liquid by the planet's own radioactive decay. In this hidden sea, completely isolated from any star's light, primitive life forms might still exist. Evolved from organisms that survived their world's ejection into space billions of years ago. Life, it seems, can find a way even in the most desolate corners of the universe, a testament to its tenacity and adaptability. The void also contains the remnants of ancient galaxy collisions. Tidal streams of stars, stretched across millions of light years, mark the paths where smaller galaxies were torn apart by the gravity of larger ones. These stellar graveyards tell the violent history of cosmic evolution, where galaxy clusters grow by cannibalizing their smaller neighbors in a process that continues to this day. We pass through regions where the cosmic web itself is visible: vast filaments of dark matter and ordinary matter that connect galaxy clusters across hundreds of millions of light years. These structures formed in the early universe, when matter first began to clump together under the influence of gravity. They are the highways along which galaxies travel, the channels through which matter flows from one region of the universe to another. The silence here is absolute, broken only by the faint whisper of cosmic rays, high-energy particles traveling at nearly the speed of light, accelerated by unknown processes in the violent hearts of distant galaxies. These particles are messengers from the most extreme environments in the cosmos, carrying tales of stellar explosions and black hole jets. They are a constant reminder that even in the quietest parts of the universe, the echoes of unimaginable power can still be heard. Our journey is not just a passage through empty space. It is a reading of a cosmic history written in the language of gravity, light, and a silence more profound than any sound. Somewhere in the cosmos, a beam of pure energy tears through space at nearly the speed of light. For just 10 seconds, it releases more power than our sun will produce in its entire 10 billion-year lifetime. This is a gamma ray burst, and it represents the most powerful explosion the universe can create. These cosmic titans occur when the most massive stars in existence, stellar giants containing the mass of 20 to 100 suns, collapse into black holes. When these monsters finally exhaust their fusion reactions, gravity wins the ultimate battle. As the star's core implodes, it fires jets of matter and energy from its poles at 99% the speed of light. The collapsing core creates a newborn black hole surrounded by a disk of superheated material. Magnetic fields, twisted and amplified by the collapse, act like cosmic cannons, launching these jets outward with impossible precision. The jets punch through the dying star like bullets through tissue paper, emerging as focused beams of destruction that remain tightly collimated across vast distances. A single gamma ray burst can outshine 1 trillion stars. If you could see gamma rays with your eyes, these explosions would appear brighter than the full moon, even from galaxies billions of light years away. The energy released in seconds exceeds what 10 trillion hydrogen bombs could produce if they exploded every second for the entire age of the universe. The most powerful gamma ray burst ever detected, nicknamed the Boat for brightest of all time, occurred in October 2022. It was so intense that it saturated gamma ray detectors across the solar system and created detectable changes in Earth's upper atmosphere from a distance of 2 billion light years. That gives you a sense of how impossibly powerful these events truly are. The light we detect traveled for billions of years, carrying news of stellar deaths from when the universe was young and stars were more massive and violent than anything we see today. Scientists have detected bursts so distant, their light began traveling when the first stars were being born, less than 1 billion years after the Big Bang. These ancient beacons give us glimpses of the early cosmos, when massive stars lived fast and died violently, seeding space with heavy elements essential for later generations of stars and planets. But compared to what lurks in the darkness between galaxies, even these titans pale in comparison. At the heart of our galaxy sits a monster 4 million times more massive than the Sun. Sagittarius A star devours everything that ventures too close, from gas clouds to entire star systems. Yet this giant is considered small compared to the true titans of the cosmic deep. Some supermassive black holes contain the mass of 40 billion suns, compressed into a region smaller than our solar system. They are like cosmic vacuum cleaners, with gravity so intense that nothing, not even light, can escape once it crosses their event horizon. Space and time bend around them like water swirling down a drain, creating distortions that would seem impossible if we did not observe them directly. These gravitational monsters did not grow slowly. The most distant quasars shone from when the universe was less than 1 billion years old, powered by black holes that somehow grew to billions of solar masses in the cosmic equivalent of a few minutes. Normal stellar evolution simply cannot explain their existence. The leading theory suggests these giants began as massive seeds formed directly from collapsing gas clouds in the early universe, containing hundreds of thousands of solar masses from the moment of their birth. When gas spirals into a supermassive black hole, friction heats it to temperatures of millions of degrees. The material forms an accretion disk that glows brighter than 100 billion stars. The disk rotates so rapidly that matter near the inner edge travels at significant fractions of light speed, experiencing time dilation effects that would stretch seconds into hours for outside observers. The most luminous quasars can be seen from across the observable universe, like cosmic lighthouses broadcasting their presence across billions of light years. They outshine their entire host galaxies, making the combined light of hundreds of billions of stars seem dim by comparison. The most violent black holes launch jets of particles at nearly light speed, creating beams that stretch for hundreds of thousands of light years. These jets carry enough energy to reshape entire galaxies, heating gas clouds to millions of degrees and preventing new stars from forming across vast regions of space. The jets can remain active for millions of years, continuously pumping energy into their surroundings. Recent observations have revealed black holes that seem too massive for their host galaxies. breaking the normal relationships between central black hole mass and galactic properties. These overmassive giants challenge our understanding of how galaxies and their central black holes evolve together. They suggest a more violent, chaotic past, where mergers and cosmic collisions played an even greater role in shaping the universe than we previously thought. Something magnificent appears in the distance as we navigate the intergalactic medium. A galaxy cluster containing hundreds of individual galaxies, each one an island universe in its own right. The Virgo cluster spans 13 million light-years across space, containing more than 300 galaxies bound together by gravity in a cosmic dance that has continued for billions of years. As we approach this stellar metropolis, the scale becomes overwhelming. Each galaxy contains hundreds of billions of stars, and many of these galaxies are larger than our own Milky Way. Some are elegant spirals with arms that sweep through space like frozen fireworks. Others are massive ellipticals that glow with the combined light of 1 trillion ancient suns. The largest galaxy in the cluster, Messier 87, dominates the central region like a cosmic giant. This massive elliptical galaxy contains over 1 trillion stars and harbors one of the most powerful black holes ever discovered. The black hole at its center is so massive that it contains the equivalent of 6.5 billion suns, and it is actively feeding on surrounding matter, creating jets of plasma that shoot out from its poles at nearly the speed of light. These jets extend for thousands of light years, creating a cosmic lighthouse that can be seen from billions of light years away. The energy released by matter falling into this black hole is so enormous that it heats the surrounding gas to millions of degrees, creating a hot, glowing atmosphere that pervades the entire galaxy cluster. Between the galaxies, we discover an invisible ocean of superheated gas, heated to temperatures of 50 million degrees Celsius by the gravitational energy of the cluster itself. This intergalactic medium contains more matter than all the stars in all the galaxies combined. Yet, it is so diffuse that it is completely invisible to the naked eye. Only our most sensitive instruments can detect its presence through the X-rays it emits as it radiates away its enormous heat. The cluster is also filled with dark matter, which makes up about 85% of all the matter here. This mysterious substance forms an invisible scaffolding that holds the entire cluster together, preventing the galaxies from flying apart despite their enormous speeds. Some galaxies are moving through the cluster at over 1,000 kilometers per second, fast enough to travel from Earth to the Moon in just 6 minutes. As we navigate through this cosmic city, we witness ongoing galactic interactions. Smaller galaxies are being torn apart by tidal forces, their stars stripped away to form long streamers that will eventually be absorbed by larger galaxies. This is galactic cannibalism on a massive scale, where the strong devour the weak in a process that has shaped the evolution of galaxies since the early universe. We witness something extraordinary: 2 galaxies locked in a gravitational death spiral, their collision unfolding over hundreds of millions of years. The antennae galaxies, once separate and distinct, are now merging in a cosmic catastrophe that will reshape both systems completely. Their spiral arms have been stretched and distorted into long tidal tails that extend for hundreds of thousands of light years. Resembling the antennae of a cosmic insect, the collision zone is a stellar nursery of unprecedented violence. Gas clouds from both galaxies are smashing together at speeds of hundreds of kilometers per second, compressing and heating the interstellar medium until it reaches temperatures where new stars can form. The rate of star formation here is 10 times higher than in normal galaxies, creating brilliant clusters of young, hot stars that burn with the intensity of blue-white diamonds. The merger is also creating something entirely new: globular clusters, dense balls of stars that will survive long after the collision is complete. These stellar cities contain hundreds of thousands of stars packed into regions just a few dozen light-years across. They are among the oldest objects in the universe, and new ones are being born in the chaos of this galactic collision. As we watch this cosmic catastrophe unfold, we realize we are seeing the future of our own galaxy. In approximately 4 billion years, the Milky Way will collide with the Andromeda Galaxy in a similar cosmic dance. The collision will take place over hundreds of millions of years, gradually reshaping both galaxies into something entirely new. The space between the colliding galaxies is not empty. It is filled with streams of stars that have been torn from their home galaxies by tidal forces. These stellar refugees will wander through intergalactic space for billions of years, no longer bound to any particular galaxy, despite the apparent violence of the collision. Individual stars rarely collide with each other. The distances between stars are so vast that most will simply be redistributed into new orbits around the merged galaxy's center. However, many planetary systems will be disrupted, their planets flung into new orbits or ejected from their home systems entirely. The collision is also creating something beautiful: shock waves that compress the interstellar medium and cause it to glow with brilliant colors. These cosmic fireworks paint the merger zone in shades of red, blue, and green, creating one of the most spectacular sights in the universe. This is the creative power of destruction, a force that tears down old structures to build new ones, a cycle of death and rebirth played out on a galactic scale. The universe is not a quiet, static place. It is a dynamic, evolving system, shaped by the constant interplay of gravity, matter, and energy. And in its most violent moments, it reveals its true, creative potential. But even these titans bow to forces that operate on scales beyond imagination. Across 13.8 billion light-years of space, an invisible force is winning a cosmic war. Every second, it pushes galaxies farther apart, stretching the very fabric of space-time itself. This mysterious power, called dark energy, makes up 70% of everything that exists. Yet, we know almost nothing about what it actually is. Dark energy is not like other forces. It does not weaken with distance like gravity or electromagnetism. Instead, as space expands, more dark energy appears to fill the void. The bigger the universe becomes, the faster it expands. It is like a cosmic gas pedal that only knows how to accelerate, growing stronger as it pushes everything apart. Scientists discovered this force by accident while studying distant supernovae in the 1990s. They expected the universe's expansion to be slowing down due to the gravitational pull of all the matter within it. Instead, they found the opposite. Space is expanding faster today than it was billions of years ago, as if some invisible hand is pulling everything apart with increasing strength. Think of the universe as a balloon being inflated by an invisible breath. Dark energy is that breath, causing every point on the balloon's surface to move away from every other point. Galaxies ride this expanding space like boats on a swelling ocean, powerless to resist the tide that carries them into the cosmic deep. The amount of dark energy in the universe increases as space expands. This seems to violate the conservation of energy, one of the most fundamental laws of physics. Yet, observations consistently show that the energy density of dark energy remains constant even as the volume of space grows. Where this extra energy comes from remains completely unknown. It is as if the universe is creating energy out of nothing, a constant, pervasive miracle that defies our most basic understanding of reality. Current theories suggest dark energy might be a property of space itself. a kind of cosmic constant that Albert Einstein originally proposed and later called his greatest blunder. He introduced it to create a static universe. But perhaps he was right for the wrong reason. It may be the intrinsic energy of the vacuum, a baseline energy level that permeates all of reality. Others think it could be a dynamic field, a form of energy called quintessence that changes over time, or even evidence that our understanding of gravity needs major revision on cosmic scales. Whatever its true nature, dark energy is the dominant force in the universe's evolution, the silent driver of its ultimate fate. It is a force that does not act on objects, but on space itself. A constant, irresistible pressure that is slowly, inexorably, pulling everything apart. The consequences of dark energy are profound and terrifying. In the far future, it will tear apart everything we see. First, galaxy clusters will separate beyond recognition, becoming isolated islands in an ocean of expanding darkness. The light from distant galaxies will be stretched to wavelengths so long that they become undetectable. Our cosmic horizon will shrink, leaving our own galaxy alone in an empty, black universe. Then, as the expansion continues to accelerate, individual galaxies will lose their ability to hold together against the cosmic tide. Stars will be stripped from their orbits, their light fading into the growing darkness. Eventually, even atoms themselves may be stretched apart in what scientists call the Big Rip. Stars will be extinguished, planets will drift away from their suns, and even the fundamental particles that make up matter will be separated by vast, uncrossable distances. Dark energy, which seems gentle today, will become the universe's final destroyer, unmaking everything that gravity and the other forces worked billions of years to create. It is a slow, patient apocalypse, a cosmic unraveling that will leave behind a cold, dark, and empty universe. The ultimate victory of emptiness over structure, of expansion over attraction. The final, silent end of everything we know. Imagine taking a mountain and compressing it down to the size of a sugar cube. The result would still be 1,000 times less dense than a neutron star. These cosmic lighthouses pack the mass of our sun into a sphere just 12 miles wide, creating gravitational fields so intense they warp light itself and bend space-time into impossible geometries. But gravity is not their most terrifying feature. Neutron stars possess magnetic fields 1 trillion times stronger than Earth's protective magnetosphere. These invisible force fields trap charged particles and accelerate them to nearly the speed of light, creating beams of radiation that sweep across space like cosmic searchlights. The magnetic field of a typical neutron star is so powerful it could erase every credit card on Earth from a distance of 600 miles. If you could somehow approach within 1,000 kilometers, the magnetic force would be strong enough to pull the iron from your blood. The field lines themselves become visible as they trap and channel streams of charged particles into narrow beams. When these magnetized neutron stars spin, they become pulsars, firing beams of radio waves and X-rays with the precision of atomic clocks. Some rotate 600 times per second, faster than a kitchen blender, yet maintain perfect timing that rivals the most accurate timepieces ever built. Each pulse marks another rotation of a stellar corpse spinning in the darkness. The surface of a neutron star is a realm of impossible physics where familiar matter cannot exist. The magnetic field is so strong, it stretches atoms into needle-like shapes aligned with the field lines. Normal atomic structure breaks down completely, replaced by exotic forms of matter that exist nowhere else in the universe. Any ordinary matter that falls onto a neutron star's surface would be compressed instantly into a layer just millimeters thick. The gravity is so intense that a marshmallow dropped from waist height would hit the surface with the force of a hydrogen bomb, releasing more energy than all the explosives used in World War II. Some neutron stars, called magnetars, have magnetic fields 1,000 times stronger still, approaching the maximum strength allowed by the laws of physics. When these objects experience magnetic quakes, their crusts crack and shift, releasing more energy in 1/10 of a second than our sun produces in 100,000 years. These magnetic cataclysms create giant flares that can be detected from across the galaxy. The most powerful magnetar flare ever recorded temporarily affected Earth's upper atmosphere from a distance of 50,000 light-years, demonstrating the incredible reach of these stellar remnants. The magnetic field around a magnetar is so intense that it affects the vacuum of space itself, causing it to become birefringent, like a crystal. Light waves become polarized as they pass through this magnetized void, providing astronomers with direct evidence of field strengths that exceed anything achievable in terrestrial laboratories. But these stellar remnants are only the beginning of nature's most extreme creations. Stretching across the observable universe are invisible threads that could slice through planets like wire through cheese. These cosmic superstrings, if they exist, are one-dimensional objects thinner than a proton, but potentially longer than galaxy clusters. They are scars left over from the birth of the universe itself, marking phase transitions in the fundamental structure of space-time. According to string theory, cosmic strings formed during the first fraction of a second after the Big Bang, when the universe underwent rapid changes in its fundamental properties. They are like cracks in a frozen pond, marking the boundaries where different regions of space crystallized in slightly different ways as the cosmos cooled from its initial state of perfect symmetry. A cosmic string just 1 meter long would weigh as much as Earth. Yet these objects are so thin, they are essentially one-dimensional, having length but no width or height in the conventional sense. They exist at the very boundary between existence and nothingness, matter and energy, reality and pure mathematics made manifest. The energy contained within a cosmic string is almost incomprehensible. A string spanning the distance from Earth to the Moon would contain enough mass energy to power human civilization for trillions of years. Yet this enormous energy is concentrated in a line so thin that it has no measurable thickness, making cosmic strings the ultimate expression of energy density. If cosmic strings move through space, they create ripples in space-time itself, generating gravitational waves that could be detected by our most sensitive instruments. When two cosmic strings intersect, they can create loops that oscillate like guitar strings plucked by the hand of the universe itself, sending gravitational waves rippling outward at the speed of light. These cosmic string loops gradually lose energy through gravitational wave radiation, shrinking over time until they eventually disappear. Some scientists believe cosmic strings could act as cosmic highways, allowing faster-than-light travel through folded space. Others think cosmic strings might be windows into extra dimensions, hidden from our three-dimensional world. These theoretical monsters remain hidden in the mathematics of physics, waiting to be discovered or disproven by future observations. 4 billion light-years from Earth, a black hole the size of our solar system is launching a beam of particles that stretches across an entire galaxy. This jet of superheated plasma moves at 99.9% the speed of light, carrying enough energy to power 1 trillion stars while maintaining perfect focus across distances that dwarf human comprehension. Quasar jets are born in the chaos surrounding supermassive black holes, where space-time itself becomes a battlefield between gravity and magnetism. As matter spirals inward towards certain doom, it forms an accretion disk spinning at incredible velocities. Magnetic fields, amplified by the disk's rotation, become twisted into configurations that store enormous amounts of energy. These magnetic field lines act like cosmic particle accelerators, channeling material from the inner regions of the accretion disk into narrow beams that shoot outward from the black hole's poles. The same gravitational forces that should drag everything into oblivion instead launch some material back into space at relativistic speeds through this magnetic catapult mechanism. The jets are so straight, they appear drawn with a cosmic ruler held by divine hands. They maintain their narrow focus across distances of hundreds of thousands of light years, threading through space with precision no human technology could match. The particles within these jets carry energies millions of times greater than anything we can create in our most powerful particle accelerators on Earth. Individual protons race along the jet at speeds so close to light that their relativistic mass increases by factors of thousands, turning ordinary matter into cosmic bullets of incredible power. When a quasar jet points directly at Earth, we see it as a blazer, and the light appears to brighten and fade as the beam sweeps past us like a lighthouse. These blazers can vary in brightness by factors of hundreds within days or hours as turbulence in the jet creates bright knots of emission traveling toward us at apparent speeds faster than light itself. This faster-than-light motion is an illusion created by the geometry of observation. When material moving at 99% light speed travels almost directly toward us, it appears to cover vast distances in impossibly short times. The effect demonstrates just how close to the ultimate speed limit these cosmic jets actually travel. The most powerful quasar jets carry enough energy to heat entire galaxy clusters, blowing bubbles in the surrounding gas that persist for hundreds of millions of years. These cosmic blowtorches can prevent new stars from forming across regions spanning millions of light years, effectively sterilizing vast volumes of space. Recent observations have revealed jets that extend far beyond their host galaxies, stretching into the intergalactic medium where they continued to propagate for millions of years. These ancient jets carry the signature of black hole activity from cosmic epochs when the universe was younger and more violent than today. In a binary star system 30 million light-years away, a white dwarf star is slowly stealing material from its companion, like a cosmic vampire feeding on stellar blood. For millions of years, hydrogen gas flows from the larger star onto the compact remnant, building up layer by layer like snow accumulating on a mountainside. But this stellar snowball is approaching a deadly threshold that will trigger one of the universe's most precise explosions. White dwarf stars are the dense cores left behind when sun-like stars exhaust their nuclear fuel and shed their outer layers. These stellar remnants pack the mass of our sun into a sphere the size of Earth, creating matter so dense that a teaspoon would weigh as much as a car. The stolen material accumulates on the white dwarf's surface, compressed by gravity into a thin shell of hydrogen that gradually builds up pressure and temperature. When the white dwarf reaches exactly 1.4 times the mass of our sun, something catastrophic happens. This critical mass, known as the Chandrasekhar limit, represents the maximum weight that electron degeneracy pressure can support. Beyond this point, the star can no longer hold itself up against its own gravity. The accumulated material ignites in a runaway thermonuclear explosion that tears the entire star apart in seconds. This is a Type Ia supernova, and it represents one of the most precisely violent events in the universe. Every Type Ia supernova releases almost exactly the same amount of energy because they all involve the same mass of material undergoing the same nuclear reaction. This cosmic standardization makes them perfect tools for measuring distances across billions of light years. The explosion shines with the light of 5 billion suns, visible from galaxies billions of light years away. For weeks, a single exploding white dwarf can outshine an entire galaxy. The explosion synthesizes and scatters elements essential for life across vast regions of space. The calcium in your bones, the iron in your blood, and the nickel in coins were all forged in the hearts of exploding white dwarf stars. You are literally made of stellar ashes, scattered by these cosmic crematoriums billions of years ago. Two city-sized objects spiral toward each other through the darkness of space, locked in a gravitational death dance that has lasted for millions of years. They are neutron stars, the crushed cores of massive stars, and their collision will create the most violent event in the nearby universe, while forging elements more precious than anything in a king's treasury. Each neutron star contains more mass than our sun compressed into a sphere just 12 miles across. As they orbit closer and closer, the neutron stars distort each other's shapes through pure gravitational force. The orbital dance accelerates as energy bleeds away through gravitational waves, ripples in space-time that stretch and compress the very fabric of reality. Advanced detectors on Earth can measure these waves even though they change distances by less than 1/10,000th the width of a proton. In the final seconds before collision, the neutron stars complete hundreds of orbits per second. When they finally touch, they create a brief flash of gamma rays, followed by a longer-lived explosion called a kilonova. The merger forges elements heavier than iron through a process called rapid neutron capture. In the extreme conditions of the collision, atomic nuclei are bombarded with so many neutrons that they can barely absorb them fast enough. This creates unstable neutron-rich isotopes that decay into stable heavy elements, including gold, platinum, and uranium. A single neutron star merger produces quantities of gold equivalent to several Earth masses. The collision ejects this stellar treasure at speeds approaching 1/3 the speed of light, seeding nearby space with materials that will eventually find their way into future generations of planets and asteroids. The kilova light comes from billions of newly created atomic nuclei undergoing radioactive decay, creating a fireball that shines with the combined light of hundreds of millions of suns. 13.8 billion years ago, everything that exists today was compressed into a point smaller than a proton. All the matter and energy in the observable universe occupied a space with no dimensions at all. This was the Big Bang singularity, and it represents the ultimate expression of cosmic power, the moment when existence itself began. At this primordial moment, the laws of physics as we understand them break down completely. Temperature and density become infinite. Space and time have no meaning. The four fundamental forces were unified into a single, unimaginably powerful interaction. In the first fraction of a second, the universe expanded faster than light itself. This period of cosmic inflation stretched space by factors of billions in less time than it takes to blink. Space did not explode into pre-existing emptiness, but rather created new space as it grew. As the universe expanded and cooled, this cosmic unity shattered. The forces separated in a series of phase transitions that released enormous amounts of energy and determined the basic structure of physical law. First, gravity separated, then the strong force, and finally, electromagnetism split from the weak force. During the first minute, the universe cooled enough for the first atomic nuclei to form through a process called Big Bang nucleosynthesis. Protons and neutrons fused together in a cosmic forge that created most of the hydrogen and helium we see today. For 300,000 years, the universe remained opaque to light, a glowing fog filled with energy. Then came cosmic dawn, Electrons and atomic nuclei combine to form the first neutral atoms, allowing light to travel freely for the first time. This cosmic clearing created the afterglow we still see today as the cosmic microwave background radiation, a faint echo of creation itself. Beyond the realm of ordinary supernovae lies something far more violent. When a star containing 50 times the mass of our Sun finally runs out of nuclear fuel, it creates a hypernova, an explosion so energetic it dwarfs regular supernova by factors of 10 to 100. Only the most massive, rapidly rotating stars can trigger hypernovae. When the core of such a star collapses, it forms a black hole almost instantly. The star's rapid rotation creates an accretion disk around the newborn black hole, generating magnetic fields of unimaginable strength. These twisted magnetic field lines launch jets of matter and energy outward at 99.9% the speed of light. The jets bore through the collapsing star like cosmic drill bits, carrying enough energy to power our Sun for billions of years. The shock wave from the jet's passage heats the star's interior, triggering explosive nuclear burning throughout the stellar remnant. A single hypernova can synthesize more heavy elements than dozens of normal supernovae, scattering them across vast regions of space. Their shock waves can disrupt star formation across entire regions of galaxies. Two massive galaxy clusters race toward each other at speeds of thousands of miles per second. When these cosmic titans collide, they create the most energetic events in the universe since the Big Bang itself. Galaxy clusters are the largest gravitationally bound structures in the cosmos. When they collide, the energy released exceeds the combined output of all the stars in both clusters by factors of 1,000,000. The hot gas that fills the space between galaxies slams into each other at velocities approaching 5,000 miles per second. The collision creates shock waves that heat the gas to temperatures exceeding 100 million degrees. These cosmic crashes can trigger the formation of radio halos spanning millions of light years and bow shocks that propagate outward at thousands of kilometers per second. During the collision, individual galaxies experience their own violent encounters. Tidal forces can strip stars from galaxy outskirts, creating long streams of stellar debris. Hidden in the quantum foam that underlies all reality, lurks a possibility so terrifying that it could end everything we know in an instant. The Higgs field, which gives all particles their mass, might not be in its lowest possible energy state. If this field suddenly dropped to its true minimum, it would create a bubble of destruction that expands at light speed, rewriting the laws of physics and annihilating everything in its path. The Higgs field permeates every corner of space, like a ball balanced on a hill. This field might currently sit in what physicists call a false vacuum state. It appears stable, but it could potentially roll down to an even lower energy level. If vacuum decay began anywhere in the universe, it would create an expanding sphere of true vacuum moving outward at exactly the speed of light. Nothing could escape. We would have no warning. Inside the bubble of true vacuum, the fundamental constants of nature would be different. Particles might have different masses or not exist at all. Atoms as we know them could not form. Chemistry and biology would become impossible. The energy difference between the false vacuum and true vacuum would be released as the bubble expanded, exceeding the rest mass energy of all matter in the universe. Current calculations suggest that our vacuum might indeed be metastable. High-energy events like cosmic ray impacts or black hole evaporation could potentially trigger the transition. Even quantum fluctuations might spontaneously nucleate a bubble of true vacuum in empty space. The terrifying aspect of vacuum decay is its inevitability if the false vacuum state exists. Quantum mechanics guarantees that any metastable state will eventually decay. Over the vast timescales of cosmic evolution, even the most unlikely events become certain. Vacuum decay would be the ultimate cosmic reset button. Everything would be erased and replaced by a universe with fundamentally different physics in the first moments after the Big Bang. Tiny fluctuations in density could have collapsed to form black holes more massive than mountains, yet smaller than atoms. These primordial black holes would possess gravitational fields so intense they warp space and time on scales invisible to the human eye. Unlike black holes formed from collapsing stars, primordial black holes could have any mass. The smallest ones would be quantum objects, where the strange rules of quantum mechanics clash with the absolute authority of general relativity. A primordial black hole with the mass of a mountain would be smaller than a proton. According to Stephen Hawking's calculations, black holes emit radiation and slowly evaporate over time. The smaller the black hole, the faster it evaporates and the more violently it dies. A primordial black hole with the mass of a large asteroid would explode with the energy of millions of hydrogen bombs. In its last second of existence, it would release more energy than our sun produces in an entire year, all concentrated in a point smaller than an atomic nucleus. If primordial black holes exist in large numbers, they could solve one of cosmology's greatest mysteries, the nature of dark matter. These invisible objects would exert gravitational influence without emitting light. The most massive primordial black holes could have served as seeds for the supermassive black holes we observe at the centers of galaxies today, solving the puzzle of how such enormous black holes could have formed so early in the universe's history, before the universe was even 1 second old. Space itself underwent the most violent expansion in cosmic history. In a period shorter than the time it takes light to cross a proton, the universe grew from smaller than an atom to larger than a grapefruit. This process, called cosmic inflation, represents the most powerful force ever unleashed, stretching space faster than the speed of light. The driving force was a quantum field called the inflaton, which filled all of space with an enormous energy density. Unlike normal matter, this field had the bizarre property of creating more energy as space expanded. Inflation solved several fundamental problems. It explains why the cosmic microwave background radiation has nearly identical temperatures in all directions. Quantum fluctuations in the inflaton field were stretched to cosmic scales, creating the density variations that would later grow into galaxies and galaxy clusters. When inflation finally ended, the inflaton field decayed into ordinary matter and radiation, reheating the universe to temperatures exceeding 10 to the 28th degrees. Some theories suggest that inflation is an eternal process that continues to create new regions of space-time beyond our observable universe. In this scenario, our entire cosmos might be just one bubble in an infinite multiverse where new universes are constantly being born. In the heart of a dying star, spinning at 1,000 revolutions per second, magnetic fields 1 trillion times stronger than Earth's are about to unleash destruction beyond imagination. This is a magnetorotational supernova, where the combination of extreme rotation and magnetic power creates explosions that dwarf even the mightiest gamma-ray bursts. When the most massive, rapidly rotating stars collapse, the conservation of angular momentum spins the core even faster. As the stellar core shrinks from the size of Earth to just 12 miles across, its rotation rate increases by millions of times. The magnetic field lines, frozen into the collapsing plasma, become twisted and amplified until they reach strengths that approach the theoretical limits allowed by physics. These fields become so powerful they can influence the structure of space-time itself. When these magnetic structures finally become unstable and reconnect, they release their stored energy in violent magnetic explosions. The combination of rapid rotation and extreme magnetic fields creates a cosmic dynamo more powerful than anything else in the universe, launching jets of magnetized plasma at velocities approaching the speed of light. The magnetic fields generated are so strong they affect the vacuum of space itself, causing it to become birefringent, splitting light into separate polarizations. Space itself becomes a kind of cosmic crystal with directional properties. The energy released by a magnetorotational supernova can exceed that of a normal supernova by factors of hundreds, synthesizing exotic isotopes that cannot be created under any other conditions. In the vast halos surrounding every galaxy, an invisible substance outweighs all the stars by a factor of 5 to 1. This dark matter feels gravity, but interacts with nothing else we understand, creating a shadow universe. But if dark matter particles ever encounter their antimatter twins, they could unleash explosions that make supernovae look like fireflies. Dark matter particles, if they are their own antiparticles, would annihilate completely when they collide, converting their entire mass into pure energy. A single kilogram of dark matter undergoing annihilation would release the same energy as 21 million tons of explosives. In the dense cores of galaxy clusters, where dark matter concentrations reach their peak, these annihilation events could create cascades of high-energy particles and gamma rays, exceeding the combined output of all the stars in the cluster. The annihilation process could create pairs of photons with energies millions of times greater than visible light. These gamma rays would carry the signature of dark matter destruction, providing a direct window into the properties of this mysterious substance. In the extreme environment near black holes, where dark matter densities can reach extraordinary levels, annihilation rates could become so high that they contribute significantly to the total energy output. The search for dark matter annihilation signals has led astronomers to examine the most extreme environments in the universe. The absence of clear signals so far suggests that either dark matter does not self-annihilate or the process occurs much more rarely than initially predicted. Somewhere in the depths of space, protons are being accelerated to energies that dwarf anything we can achieve on Earth. These cosmic ray particles race through the galaxy at 99.9999% the speed of light, carrying individual energies equivalent to a baseball thrown at 60 miles per hour, compressed into a single atomic nucleus. The most energetic cosmic rays detected on Earth carry energies exceeding 10 to the 20th electron volts, more than 10 million times the energy achievable in the Large Hadron Collider. The cosmic accelerators responsible for these extreme particles remain one of astrophysics' greatest mysteries. Active galactic nuclei, powered by supermassive black holes, represent the most likely candidates. The magnetic fields near these objects can store enormous amounts of energy, launching jets that create natural particle accelerators millions of light years long. The most extreme cosmic ray events might involve entirely different acceleration mechanisms. Some theories suggest that the decay of exotic particles left over from the Big Bang could produce cosmic rays with energies exceeding anything possible through conventional acceleration. In the apparently empty space between atoms, between planets, between stars, the quantum vacuum seethes with invisible activity. Virtual particles pop into existence and annihilate each other in time so brief they exist below the threshold of direct observation. Yet these quantum fluctuations contain enough energy to power the entire observable universe. The quantum vacuum is not truly empty, but filled with zero-point energy that exists even at absolute zero temperature. Calculations suggest that the energy density of quantum vacuum fluctuations should be 10 to the 120th times larger than the observed energy density of the universe. This enormous discrepancy, known as the cosmological constant problem, represents one of the greatest failures of theoretical physics. Yet quantum vacuum fluctuations do produce measurable effects. The Casimir effect demonstrates that two metal plates placed very close together will be pushed toward each other by the pressure of virtual particles. Virtual particles near the event horizons of black holes can become real through Hawking radiation. In the early universe, quantum vacuum fluctuations were stretched to cosmic scales during inflation, becoming the seeds of all large-scale structure. Some theories suggest that our entire universe originated from a quantum vacuum fluctuation, a brief deviation from nothingness that somehow became permanent. Beyond the edge of our observable universe, beyond the most distant galaxies we can ever hope to see, lies something that dwarfs all the cosmic forces we have encountered. If the multiverse exists, our entire universe, with all its supernovae, black holes, and gamma-ray bursts, becomes nothing more than a single bubble in an infinite ocean of realities. In the eternal inflation scenario, our Big Bang was not a unique event, but one of countless explosions occurring continuously throughout higher dimensional space. New universes are constantly being born as quantum fluctuations trigger inflation in regions of false vacuum. Each universe within this multiverse could have completely different fundamental constants. In some, gravity might be stronger or weaker. In others, the electromagnetic force might have different strength, making atoms impossible. The total energy contained within an infinite multiverse would literally be infinite. Some regions of the multiverse might contain universes that expand forever, while others collapse back on themselves in big crunches. In certain interpretations of quantum mechanics, the multiverse consists of all possible outcomes of quantum measurements existing simultaneously in parallel realities. Every time a quantum event occurs with multiple possible results, the universe splits into separate branches. The anthropic principle suggests that we observe our universe's particular combination of physical constants, because only this combination allows observers like us to exist. In a multiverse containing all possible combinations, conscious beings would necessarily find themselves in universes capable of supporting consciousness. We have journeyed from the quantum realm to the infinite multiverse, witnessing forces that stretch the very limits of what reality can contain. The most remarkable truth we have discovered is that the universe does not simply contain power. It is power. Every atom in your body exists because forces beyond imagination hold it together. Every star that lights the cosmic darkness burns because nuclear forces convert matter into pure energy. Every galaxy spins through space because gravity and dark energy wage their eternal war. But perhaps the most profound realization is that we, as conscious observers, are not separate from these cosmic forces. We are their direct products. The calcium in our bones was forged in stellar explosions. The iron in our blood was scattered by dying stars. The gold in our jewelry was created when neutron stars collided. We are literally made of stardust, assembled by forces so powerful they can create and destroy entire worlds. Yet here we stand, conscious beings capable of contemplating our own cosmic origins. Proof that the universe's greatest power may not be its ability to destroy, but its capacity to create complexity, beauty, and ultimately, awareness itself. The universe has been working for 13.8 billion years to create the conditions necessary for you to exist. Every force we have explored played a role in bringing about this moment. What is the most powerful thing in the universe? Perhaps it is not any single force, but the universe's inexhaustible creativity. Its ability to transform simple hydrogen into stars, stars into heavy elements, elements into planets, and planets into the stage where life and consciousness can emerge to contemplate the very forces that brought them into being. The universe's most powerful force may ultimately be its capacity to know itself through beings like us. In understanding cosmic power, we become the universe awakening to its own magnificent potential.